approach we've taken so far is exact for all fields. In particular, these results model absorption saturation. If we keep trying to absorb more photons into an ensemble of these atoms, there will be fewer and fewer atoms in their lower states, and also more and more in their upper states. The atoms in their upper states cannot absorb anymore. That means that those atoms no longer participate in the optical absorption process, so we expect the strength of the absorption to decrease. As we excite more atoms into the upper state, they also start to show stimulated emission from the upper to the lower state, which is included in this model. Hence, absorption disappears as we go to higher intensities, with this model correctly showing a limit of equal upper and lower populations at high intensities. Note incidentally that there's no amount or intensity of light that we can apply at this absorbing frequency that allows us to invert the population, that is, to have more atoms in their upper state than in their lower state.
So, in this expression here, we note, of course, as we said before, that omega squared is proportional to the electric field squared, the optical electric field we're applying here, and that in turn is proportional to the intensity of the light. Hence, we can write, instead of 4 omega squared T2 T1, we can write the intensity divided by some parameter we could call the saturation intensity. Hence, for example, if we were exactly on resonance, where omega, the applied frequency, was equal to the transition frequency, we would have that the imaginary part of the susceptibility, essentially the absorption strength, would follow this kind of formula. So we'd have a proportionality constant out front, but we'd be left with this as all of this factor here. And that equation describes what's called absorption saturation, often seen at the high intensities from lasers. So if we kept increasing this intensity here, this denominator would get larger and larger and larger, which would mean that the absorption would get smaller and smaller. As we drive a transition like this very intensely, then the absorption progressively disappears. That's actually happening because we are progressively making the populations of the upper and lower states equal to one another. And in that situation, there is no absorption left because the process to absorb going up is equal to the process to emit by actually stimulated emission going down.
So far, we showed an exact solution of a simple problem, including both the linear response and the nonlinear response of absorption saturation. Just as in direct solutions of Schrödinger's equation, for many other problems, exact solutions are usually not possible either when using the density matrix formalism. Just as for Schrödinger's equation, though, we can use perturbation theory here too.
So we could also try to set up a perturbation theory, but based on a density matrix description of a system. The idea here of the perturbation theory is not fundamentally different, it's just that we're writing the rest of the quantum mechanics using the density matrix. So now we would start with this equation we deduced for the time behavior of the density matrix instead of Schrödinger's equation. And we could also generalize the relaxation time approximation, now writing a proposed set of relations where we have introduced these additional terms for each one of the possible density matrix elements. So now we would have that rho mn naught is the equilibrium value for rho mn, and gamma mn is its relaxation rate, or 1 over the time associated with what we'd think of as the relaxation of this density matrix element back to its equilibrium value. One then starts with equations like this one, instead of the time-dependent Schrödinger equation, and constructs a perturbation theory just as before. This density matrix version is the one commonly used for calculating nonlinear optical coefficients, eliminating the singularities when the transition energy and the photon energy coincide. So we won't do that here, But essentially, it's the same kind of construction we would end up doing, just with somewhat different algebra and a somewhat different description.